Hey everyone, and welcome to Pre-Calculus Lecture 14, Part 2. We have a few more things with quadratic functions that we need to do before we go to quadratic inequalities. The first thing that we're going to do is we're going to take the graph of a parabola and try to figure out the function that generates this graph. We might be asked to do it this way. Determine the quadratic function whose graph is given below. And here's the graph. Now, just how in the world are we going to do this? Here's what I think. I think we need to do it this way, and I'll tell you why. This is the form that we like. We can look at this form of a quadratic function, and we can say, aha, the axis of symmetry is h. And then we can say, aha, the vertex is the point xy equals hk. Well, let's see, we know what the vertex is, right? So we pretty much know what h and k are already. And see, this is nice too because we know one thing already. A should be positive because this graph is opening upward. So let's get to work on this. And I think the first thing that I'm going to do is I'm going to write the axis of symmetry. I'm going to put it right here. This line goes right through the point -1, -2. And on a vertical line, the x-coordinate of every point is the same as the x-coordinate of every other point on that line. So if we know the x-coordinate of one point on that line, we know the x-coordinate of every point on this line. And that equation, x equals the x-coordinate, that equation is actually the equation of this line. So let's see, we have our axis of symmetry. And that's always of the form x equals h. So guess what? We've got h. We kind of knew that anyway, but we have h. Now the vertex. The vertex is the ordered pair that gives this point right at the bottom. -1, -2. The vertex is the point hk. So maybe I could have written it this way. So we know H and we know K. H equals -1. K equals -2. The only thing that we need to know about our function that we don't already know is A. So let's write down what we have already. That we have f of x equals A times x minus h squared, x minus h squared, plus k. Here's our quadratic function. The only thing that we don't have is the value of A. Here's f of x. F of x equals A quantity x plus 1 squared minus 2. To find the value of A, plug in the coordinates of a point on the parabola other than at hk. We've already plugged these values into the equation for the parabola. We need a different point. And here's a point on the graph, 0, -1. We propose to plug in the coordinates of this point into our equation, f of x equals ax plus 1 squared minus 2. This is a known point on the parabola, xy equals 0, comma -1. Plug these values in for x and y. And by the way, do we see a y in that equation? We don't, do we? Or do we? We don't literally see a y here. But in the context of a function f of x, what is y? Aren't y and f of x the same thing? So this y coordinate, -1, this is what we're going to plug in for f evaluated at x when x is 0. And we'll do it this way. The y coordinate, -1, is equal to f evaluated at x equals 0. You see that? So we've taken -1 and plugged it in for y. And we've taken 0 and we've plugged it in for x. And we're also going to take 0 and plug it in for x over here. X, but x is 0, plus 1 squared minus 2. So we have 0 plus 1 squared is 1 times a minus 2. Okay. -1 equals this thing, which equals this thing, which equals this thing. We have -1 equals a minus 2. Or a minus 2 equals negative 1. And that means if we add 2 to both sides, we're going to get a equals 1. And I'm going to take that value for a and I'm going to put it right back here. We've got a. We're going to put that into the definition of f of x. And when we substitute a equal 1 into this definition for f of x, here's what we get. F of x equals 1 times x plus 1 squared minus 2. But usually when we have a factor of 1, we don't mention it explicitly. So here's how we're going to write it. That was pretty good. Let's do another one. This one's kind of similar to the last one. But we have the graph of a parabola. So it represents some quadratic formula. And they tell us, determine the definition of the quadratic function whose graph is given below. And look at what we have. Here's our axis of symmetry. It passes through the point 2 on the x-axis. So the equation of this vertical line is x equal 2. So I know that already. In general, the equation of the axis of symmetry is x equal h. Here, the axis of symmetry is given by the equation x equals 2. So h and 2 have to be one and the same thing. Now, what else do I know? The high point or the low point of a parabola is the vertex. So this is the vertex. In general, the vertex is the ordered pair xy equals hk. And in this case, that's x equal 2, y equal 1. So we have h equal 2, and we already knew that, didn't we? But we also have k equal 1. H equals 2, k equals 1. F of x equals a x minus h squared plus k. And guess what? We just substitute in 2 for h and 1 for k. and we're looking pretty good. The only thing that we don't know is A. What are we going to do about it? Probably the same thing we did in the last example. We're going to plug the coordinates of a point on the graph other than HK. So we're going to plug the coordinates of a point on the graph other than HK into the function f of x equals a x minus 2 squared plus 1. And we'll solve for a. Well, here's our point, x equals 0, y equals 5. And remember, y and f of x are the same thing. So this is saying that when x is 0, y or f of x equals 5. So let's write that down. 5 equals f evaluated at 0, plugging in 0 for x, and that equals a times 0 for x minus 2 squared plus 1. So we have negative 2 squared is 4 times a, so that's 4a plus 1. Five is our y coordinate, and f equals 0 is our y coordinate. 5 equals f of 0, which equals this thing, which equals that thing. Okay, subtract 1 from both sides. 4 equals 4a. You know what? I'll just switch this around and divide by 4. Son of a gun, a equals 1 again. This isn't always going to happen. It just happened to happen in both of our examples. Now, let's do what we set out to do. Determine the definition of the quadratic function given by that graph. Here's our function, f of x equals a times x minus 2 quantity squared plus 1. And Remember, we just identified what a was. A is equal to 1. So our quadratic function becomes f of x equals 1 times x minus 2 quantity squared plus 1. But typically we don't explicitly write a factor of 1. So we'll just say f of x equals x minus 2 squared plus 1. Let's do a couple of different examples. Here's an example kind of like what we have in our textbook. Determine without graphing whether the quadratic function has a maximum value or a minimum value, and then find that maximum or minimum value. Well, every quadratic function has a graph that's a parabola. And every parabola either has a high point or a low point, but not both. And whether it has a high point or a low point depends on the coefficient of x squared. The coefficient of x squared is always going to be a. A is equal to 4, but more important than that, a is positive. If a is positive, what does that tell us about the graph? The graph opens upward. Now, they told us not to graph, but I'm going to draw a quick graph anyway. Here's what our parabola looks like. It opens upward, and right there at the vertex, the y value is going to be the minimum value. It's going to be the minimum value because this is at the bottom of the curve. This is the y coordinate is the smallest value that the function attains. Oh my goodness, now how do I find that y value? The graph opens upwards, so the function is going to have a smallest value. And it's going to happen right at the vertex. Now, how do we find that smallest value? Well, remember this. Given a quadratic function in standard form, and that's what we got right here, f of x equals ax squared plus bx plus c. The axis of symmetry is given by x equal negative b over 2a. And the vertex has as its x-coordinate negative b over 2a. And as its y-coordinate, f evaluated at negative b over 2a. So let me just go back to the definition of our function and identify a and b. A is 4, b is negative 8. We're going to get the x-coordinate of our vertex, negative b over 2a. So that's negative. B is negative 8 over 2 times a. A is 4. Oh my goodness, this is going to be easy. Easy, easy, easy. Negative times negative is positive. And I thought it was going to be easy. If I put in the right numbers, it's going to be easy. On the bottom, we have 2a, and a is 4. I'm sorry, I didn't mean to cause you anxiety. Negative times negative is positive, so we have positive 8 divided by positive 8 is 1. So negative b over 2a is equal to 1. And now we want the y coordinate of our vertex, f evaluated at negative b over 2a. F evaluated at 1. We just plug it right in here. 4x squared minus 8x plus 3. So what do we got? 4 minus 8 is negative 4 plus 3 is negative 1. And continuing up here, the x coordinate of our vertex is 1. And I said one thing down here and I did something else. Let's do this again. 4 minus 8 is negative 4 plus 3 is negative 1. Okay, much better. Our vertex is xy equals 1, negative 1. So this is what our graph looks like. Where's the smallest y value on this graph, and what is it? Isn't it right here at the bottom where y equals negative 1? Cool. Yep. The value of our maximum value or our minimum value is going to be the y-coordinate of the vertex. The y-coordinate of the vertex will either be our maximum value, if the graph looks like this, or it's going to be the minimum value if the graph looks like that. Now, let's get on to quadratic inequalities. Just a few warm-up exercises before we start doing quadratic inequalities. Here we have the graph of a function, y equals f of x. And keep in mind, throughout pre-calculus algebra, when we talk about y and we talk about f of x, they're one and the same thing. When we say y, we mean f of x. When we say f of x, we're talking about y. So here's the graph of y equals f of x, and we're asked to find where f of x is negative, less than 0. Well, since y and f of x are the same thing, then f of x is going to be negative exactly where y is negative. And here we have the y-axis. Here we have the x-axis. Here's the origin, 0, 0. If we start at the origin and go down 1 unit, this is y equal -1, isn't it? If we start at the origin and go up 1 unit, this is y equal +1, isn't it? So we learned something that we already knew it, but we see it in a different light now. All of the points in the xy plane that lie below the x-axis have a negative y coordinate. In the xy plane, below the x-axis, y is negative. So when we're asked to determine where f of x is less than 0, we should say this. Determine the intervals on the x-axis where f of x is less than 0. That's what we really mean. Or determine the x values where f of x is less than 0. And here's what I see. I see that between x equal -2 and x equal +2, the graph of f of x is below the x-axis. Between x equal -2 and x equal +2, the graph is below the x-axis. So throughout this entire interval, from -2 to +2 on the x-axis, f of x or y is negative. So here's my answer. F of x is less than 0 on the interval -2, +2. And notice this is an open interval. I didn't include the endpoints. And the reason I didn't include the endpoints is because the endpoints are right here on the x-axis. And when x is -2, y is 0, right? So when x is -2, y isn't negative, y is 0. And when x is +2, y or f of x isn't negative, f of x is 0. So I don't include -2 and +2 among those x values that make the function negative. Now, let's do a couple more examples using this exact same function. A similar problem, determine where f of x is positive, greater than 0. Or determine the intervals on the x-axis where f of x is greater than 0. In our last example, we already saw that f of x is less than 0 between x equal -2 and x equal +2. Between x equal -2 and x equal +2, the graph of f of x is below the x-axis, so f of x is negative. So it stands to reason that when f of x is positive, the graph of f of x is above the x-axis. And here's what I see. This graph's going to keep on going like that. So really from -infinity to x equal -2 on the x-axis, the graph of f of x is above the x-axis, so f of x is positive. So on the interval from negative infinity to negative 2, the graph of f of x is above the x-axis, it's positive. And also, from x equal 2 to infinity on the x-axis, the graph is above the x-axis again. So on the interval from x equal 2 to infinity, f of x is positive. And I'll put a little union symbol here to show that both of these constitute part of the solution for our question. Again, I don't include x equal 2 as being part of the solution because when x equals 2, f of x is 0. So f of x is not positive when x is 2. And similarly, when x is negative 2, f of x is 0. So f of x is not positive when x is negative 2. Now, let me do one more thing with this example. Yeah, we're going to milk this baby for all it's worth. But first, I'm going to change it. Determine where f of x is less than or equal to 0. Wherever the graph is below the x-axis, f of x is negative. So again, the graph lies below the x-axis from x equal negative 2 to x equal positive 2. But here we say, determine where f of x is less than or equal to 0. Right here at x equal negative 2, f of x is equal to 0. So negative 2 is part of the solution this time. And we include this square bracket, which tells us that this endpoint, negative 2, is part of the solution. Similarly, when x equals positive 2, f of x is less than or equal to 0 because at x equal positive 2, f of x is 0. So x equal positive 2 is part of our solution. And we include this square bracket to show that x equal positive 2 is part of our solution. So in this case, for every x value from x equal negative 2 to x equal positive 2, f of x is less than or equal to 0. Solve the inequality. In other words, we want to know the x values such that x squared plus 3x minus 10 is greater than 0. We want to find the x values that make this true, or another way of saying this, find the intervals on the x-axis such that the x values in those intervals make this inequality true. And here's the way our authors in our text want us to do this. They want us to say, see this thing here? That's f of x. And we're going to graph f of x. And I think the first thing that I want to do, I want to find the x-intercepts. And it turns out that when we're doing quadratic inequalities, the x-intercepts are pretty important. So let's see, we want to know essentially we want to find x when f of x equals 0. So we want x squared plus 3x minus 10 equals 0. Oh, does this factor? Maybe. Let's see. I have a little bit more confidence than I did a minute ago. Factors here may be 2 and negative 5 or plus 5 and negative 2. Yeah, I think so. Plus 5, negative 2, I think that's it. We get plus 5x minus 2x is 3x. And 5 times negative 2 is 10. Perfect. So we have x plus 5 equals 0, or x minus 2 equals 0. So x equals negative 5, or x equals 2. X-intercepts. We got 2 points on the graph. And here's why knowing the x-intercepts is such an important thing when we're doing a quadratic inequality. When we're solving a quadratic inequality, we want to know where this is positive or we want to know where this is negative. And think about it. Where the quadratic expression is positive, that's where the graph is above the x-axis. Where the quadratic expression is negative, that's where the graph is below the x-axis. And right where this quadratic function changes from being positive to negative or negative to positive, that's where the graph intersects the x-axis. So these 2 points, x equal negative 5 and x equal 2, the x-intercepts, these are the points where our f of x is going to change sign from positive to negative or negative to positive. That's why when we started out, we went right for the x-intercepts. These were the important things in doing an inequality for a quadratic function. Now, the next thing that I want to do, I want to find the vertex. The next thing that I do is I want to find the vertex. So to solve this quadratic inequality, I decide I want to graph the function f of x. I want to find the x-intercepts, and I want to find the vertex. And notice the x-coordinate of the vertex is also the x-coordinate of the axis of symmetry. And parabolas are symmetric about the axis of symmetry. We have 2 points that are on the graph, and these 2 points have to be symmetric about the axis of symmetry. Now, I can find this value, negative b over 2a, just by taking B equals 3 and A equals 1. And computing negative B over 2A. But now there's another way of doing this. Look at these 2 points. How far apart are they? 2 minus a negative 5, isn't that 7 units? These 2 points are 7 units apart. And right smack in the middle is going to be the axis of symmetry. Well, let's see, what's half of 7? 7/3? No, I don't think so. 7 halves, or 3 1/2. Halfway between here and here, we go 3 1/2 units. 1, 2, 3 1/2. This is our axis of symmetry. Four, 3, 2, 1. Okay. So the axis of symmetry, x equals negative 3 halves. Now, if we had taken negative b over 2a, let's see, b is 3, and a, well, we just have x or 1x, so a is 1, right? Okay. Negative b over 2a is negative 3 halves. So one way or another, we figured this out. We either said, you know what, we've got the 2 intercepts, and halfway in between, at x equal, let's see, halfway in between, so 3 1/2 units, 1, 2, 3 1/2, right here. That's at negative 3 halves. We have the axis of symmetry. And that's got to be the x-coordinate of the vertex. But we could also do it this way, negative b over 2a. B is 3, and a is 1. So again, we get x equal negative 3 halves. That's our axis of symmetry. That's also negative b over 2a. F of negative b over 2a is f of negative 3 halves. And what does that equal? We've got to plug in 3 halves for x. Negative 3 halves. Negative 3 halves squared plus 3 times negative 3 halves minus 10. Holy moly, what is this? 9/4 minus 9 halves minus 10. Holy moly. Let's see, this is negative 9/4. And 10 is negative 40/4. So negative 49/4. Yikes. 49/4. So that is almost negative 25. Son of a gun. X equal negative 3 halves. Negative 49. Oh, wait a minute. 49/4. That's not 25. What is it? Oh. Negative 12 1/4. Okay. We can actually plot that. 1, 2, 3, 4, 5, 6, 7, 8, 9, negative 49/4. Now, why was it so important for us to find the vertex? Essentially, it told us where the graph was going to be below the x-axis and where the graph was going to be above the x-axis. We had the two x-intercepts, and the vertex was going to be halfway in between. But was the vertex going to be above the x-axis, or was it going to be below the x-axis? Now that we've drawn the graph of f of x equals x squared plus 3x minus 10, we can finally answer our question. And you know what? I'm going to redo this because I don't like the way they do it in the book. But let's just finish this first of all. Notice the graph lies below the x-axis between x equal negative 5 and x equal 2. So f of x is less than 0 on the interval negative 5, positive 2. So there's our solution. And you know what? I think we did a lot of work for nothing. This is how they'd have us do it in the book. And I like the first two steps. Getting the x-intercepts is important. But let's redo this. Yeah, let's redo this. We want to know where this thing, oh, wait a minute. We wanted to know where this is positive. Well, let's see, our answer was wrong anyway. I found out where this is negative. That's okay. We're going to redo this, but let's not do it the book's way because we did a lot of work. And we worked with a lot of messy numbers and we really didn't have to. Graph this baby. First thing, find the x-intercepts, and we get them. X equals negative 5 or x equals negative 2. And here are the x-intercepts. The axis of symmetry is going to be halfway in between, somewhere around here. And exactly where, we don't need to know. Somewhere between the x-intercepts, we're going to have the axis of symmetry. The easy way to do this is just to look at A. What is the coefficient of x squared? What is the coefficient of x squared? We don't see any, do we? That's because the coefficient is 1. The coefficient of x squared is 1. And what do we know about A? What does that tell us about the graph of a parabola? If A is positive, the graph opens up. If A is negative, the graph opens downward. Well, A equals 1. A is greater than 0. So the graph opens upward from the vertex. Now, if the vertex is up here and the graph opens upward, Is the graph ever going to intersect the x-axis? No. So the vertex can't be up here. If the vertex is down here below the x-axis and it opens upward, is it going to intersect the x-axis? It sure is. So the fact that the graph opens upward and intersects the x-axis at these 2 points means that the vertex has to be below the x-axis. So, and let me answer this question correctly this time. F of x equals x squared plus 3x minus 10 is greater than 0 wherever the graph is above the x-axis. Well, the graph is above the x-axis from negative infinity all the way to negative 5. Negative infinity to negative 5. And the graph is also above the x-axis over here from x equal 2 to infinity. Okay. You know, I like that way of solving a lot better. Anytime we have x-intercepts, just think about what A is. And if A is positive, the graph opens up. If A is negative, the graph opens down. We don't have to compute the coordinates of a vertex. This is a nice one. Let's do that one. Graph the inequality. Well, you know what? I'm going to have to rewrite this and get 0 on one side. So I'm going to move this 40x over here and make it negative 40x. Whoops, whoops, whoops. So take 40x, move it over here, it becomes negative 40x. And we have less than 0. And find the x-intercepts. Okay. So that means we find the x values when f of x equals 0. So we have 25x squared minus 40x plus 16. Here's our f of x equals 0. And, you know, this looks like a perfect square. It is. That looks like a perfect square. You know, I think I know where this is going. I think that's how it factors. Let's see. If I take the first thing and square it, I get 25x squared. If I take the second thing and square it, I get plus 16. And if I take the first times the second, which is negative 20x, and I double it, I get negative 40x. Yep, that's exactly what this thing is. It's this thing squared. Son of a gun. So let's see. When is this equal to 0? We have 5x minus 4 equals 0. So 5x equals 4. and that means x equals 4/5 x-intercept. Now we only have one x-intercept. So that tells us a few things. If this graph crosses the x-axis and goes above, if this graph is above the x-axis and crosses the x-axis, it can't come above the x-axis again someplace else because it only touches the x-axis at one point. There are a few things that we can reason on here. One thing is, this is our function rewritten. F of x is 5x minus 4 quantity squared. So f of x is a perfect square. And it's equal to 0 when x equals 4/5. But can it ever be negative? Can we square a real number and have it be negative? No. So this graph never goes below the x-axis. And there may be something else that I want to tell you too. I don't know if I want to tell you that or not. But look at what we have. We have the only point at which the graph touches the x-axis. And we know that this thing can't be negative. So the rest of the graph has to be above the x-axis. No part of this graph can drop below the x-axis. And this is the only part of the graph that touches the x-axis. So the rest of the graph has to be above the x-axis. See, there's no part of the graph that's below the x-axis because this thing can't be negative. This is the only x value where the graph touches the x-axis. We only have one x-intercept. So there can't be any points other than this one that touch the x-axis. There can't be any points on the graph that go below the x-axis. So the rest of the graph has to be above the x-axis like that. And it makes sense. Let's look at our quadratic function again before we actually factored it. Look at what A is. A is 25. Now, what's significant about that? Just the fact, what's significant? Just the fact that it's positive. So the graph opens upward. So we're trying to solve this inequality, but that's the same as this inequality. Son of a gun, where is f of x less than 0? Where does this graph ever go below the x-axis? It doesn't. So we might say no solution. Or if they have this thing called an empty set as a possible answer, this is the same as no solution. Here's a good one. Solve that inequality. So first thing, graph the inequality. And second thing, find the x-intercepts. So the graph of f of x will intersect the x-axis whenever f of x equals 0. So we find the x values that make f of x equal to 0. We set f of x equal to 0. And let's see. The only factors we have are 5 and 1. And x plus 5 times x plus 1 does not give us 2x in the middle. I think this is one of those things where we have to use the quadratic formula. The coefficient of x is 1. So a equals 1. B equals 2. C equals 5. Cool. And we have x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And we have 4 minus 20 is negative 16 over 2. Up. And you know what? We have a negative under the radical. So we have no real number solution. And you know what? On the x-axis, all we have are real numbers. If there's no real number solution, then there are no x-intercepts. Well, what does that mean? It means the entire graph of this function either lies completely above the x-axis or it lies completely below the x-axis. It's got to be one or the other. And again, the easy thing to do is to use our friend A. A is 1. And the important thing about that is that A is greater than 0. The graph opens upward. It's concave up. So let's see. Let's just see. And let me write this exercise down before I forget what it was. Okay. Is it possible that the entire graph of the function could lie below the x-axis? Well, let's see. It's got to have a vertex, so here's the vertex. And since A is greater than 0, the graph opens upward from the vertex. Uh-oh, we have x-intercepts. But we already found out there are no x-intercepts. If the graph lies below the x-axis and the graph opens up, there are going to be x-intercepts, and this can't happen. This is concave up because A is greater than 0. So impossible. The graph can't lie below the x-axis, so it has to lie entirely above the x-axis. Here's our vertex. There's the graph lying entirely above the x-axis. And notice A is greater than 0. The graph opens upward. It makes perfect sense. If the graph lies above the x-axis and A is greater than 0, that means the graph opens upward. This is what it's going to look like, and it never crosses the x-axis. So this is what happens. The graph lies entirely above the x-axis, and that means that f of x equals x squared plus 2x plus 5 is greater than 0 for all values of x. Solution, negative infinity to positive infinity. Any x value in this interval is a solution. Now, let's just consider a what if for the sake of example. We're done with this example. But suppose that the exercise had been this. X squared plus 2x plus 5 less than 0. The graph lies completely above the x-axis. So if this were the exercise, could we have any solutions? Would any x value be a solution of this inequality? No, because for all x values, the graph lies above the x-axis, which means that for all values of x, this thing is positive. It's impossible for this thing to be negative. So if this had been the original exercise, x squared plus 2x plus 5 less than 0, in that case, we'd have no solution. But just in case you joined late, this was the example. Find the set of x values such that this thing is greater than 0. And every x value between negative infinity and positive infinity is a solution.